Podcast is now starting. All attendees are in listen-only mode.
Yeah, Paul, you can jump right in.
Thank you very much. Good afternoon, everybody, and welcome to our next episode of Just Ask Paul. So today I have a series of questions, and we'll jump right into it. First off, my name is Paul Brancleon. I'm the Director of Research Education Technology here at the North American Die Casting Association. And we're going to answer several questions from die casters that I've received. The last question is rather interesting. We'll wait till we'll get to there, but not a typical die casting question. But jumping right into it, question number one is from a die caster, and their question is looking to see if NADCA has any thoughts on corrosion performance of ADC-12 die cast versus 6061 machined. Our view is 6061 cannot be die cast. Is this accurate? Would also like to see if there is a die cast aluminum grade that would be equivalent to 6061 machined aluminum. So I kind of broke this question down into a couple points. And the first one is going to be, what are die castable alloys? What makes a die castable alloy? And then I'm going to talk about corrosion resistance of those alloys. So as we start looking at casting or alloys in general, 6061 is aluminum, obviously. And those alloys are considered the 6000 series, 6XXX series type alloys. And they typically exhibit poor castability. Okay, so these 6000 series alloys are not typically used for die casting because of their poor castability. Today's market, we have castable alloys in the 300 range. So your 380, 380.1, 360, 390. All of those alloys use silicon to obtain good fluidity and good castability. There's other elements inside those 300 series alloys, such as copper, magnesium, and iron. And those are used to prevent hot cracking at elevated temperatures, add some additional strength, that's the magnesium, and reduce soldering on the die surface. That's going to be the iron content. So those 300 series alloys, make good castable alloys. There are other alloys that are still in that 300 series as far as chemistry, but those are considered structural alloys, and they use manganese and strontium, and then they lower the iron content to prevent soldering, improve elongation over those standard 300 alloys, over the 380, 360, 383 type alloys. So for high pressure die casting, our alloys have to have certain characteristics to be industrially a viable alloy. They've got to have good fluidity, and that's because we want to be able to fill the mold and have long flow distances. They have to have good hot tear resistance, so good strength at elevated temperatures. So as the casting is solidified, we're not starting to see cracking, or if we're ejecting the casting at that ejection temperatures, 500, 600 degrees Fahrenheit, we want to have that higher strength, and that's to avoid high scrap rates. And then they've got to have good die soldering resistance to avoid any excessive die wear on the tool itself and the components, and prevent repairing the tool all the time. Now, with all that said, there have been experimental alloys. I'm going to go through some of those experimental alloys right now. And these alloys actually use a 2% nickel level. And then they vary the silicon, and they can then make these die castable alloys. So if you want to see these particular alloys and get more information, this particular alloy set is from a paper from 2019 from F. Brenton, and the paper's number is T19092. And we can see that we have nickel. Here's the nickel level. So we have silicon, magnesium, nickel, iron, manganese, titanium, boron, and vanadium. So here are the nickel levels. And the nickel levels pretty consistent, right around 2%. And then what they do is they vary the silicon levels. So from very low silicon to higher, not near higher what we would consider in our 380 or 360 alloys. And then they also vary the magnesium content. So let's look at what that does to these particular alloys. And once again, these are experimental alloys. I personally don't know anybody that's running these type of alloys. But according to the paper, and once again, I've listed the paper here at the bottom of the screen. According to this paper, these alloys are all castable. So this is a graph, and this is showing the ultimate tensile strength, the UTS, of the alloys, starting with lower silicon to higher silicon. So our silicon increases as we move across this graph. And then this becomes the ultimate tensile, and you can see ultimate tensile starts to increase as we increase the silicon content. Also the yield strength, as we move the silicon level up, as we start to increase silicon levels, we see the yield strength increasing. What we also see is the elongation. So this is the elongation, and the elongation drops as silicon levels increase. Remember, they're holding these alloys at that 2% nickel level. So now we can see ultimate tensile yield and elongation for these experimental alloys. So how do these compare to 6061 alloy? So 6061, and this is now the mechanical properties. These three stars represent those mechanical properties. So this is the elongation. So the elongation is right around 25% for 6061. It's around 125 to 130 ultimate tensile, and it's just under 100 megapascals for yield. So we can see that at these silicon levels, we're represented with tensile and yield similar to 6061, but the elongation is much higher than any of these die-cast alloys. So the highest they achieved was 19%. And if we were going to use structural alloys, so Oral 2, Oral 5, those type of alloys, B360, we can achieve 13 to 18% elongation with higher silicon levels. If we were using those high silicon alloys, they also have the ability to achieve high elongation. So it really depends on mechanically what you're looking for. Are you looking for something that's going to mimic all the features of a 6061? Once again, these type of alloys would. One other comment that the paper makes is on electrical conductivity. So here we can see that, once again, the silicon content drops, and our electrical conductivity also drops. So the lower silicon levels here at this at the lowest silicon level for this 2% nickel material has the highest electrical conductivity. So if electrical conductivity was one of the features we needed to have, we would need to have this nickel alloy at its lowest silicon levels. So that's some experimental alloys that are very similar mechanically. Now let's talk about corrosion resistance. So once again, I've got the chemistry here. So this is the chemistry for 6061. 97% aluminum, has some chromium, 0.04 to 0.35, has low copper, 0.15 to 0.4, has a 0.7 iron level, 0.7%. Magnesium is held 0.8 to 1.2, manganese at 0.15, silicon 0.4 to 0.8, titanium, zinc, and then no nickels, tin, or strontium. So we can see that's in the raw 6061 alloy. Now comparing that to these castable, die-castable alloys, you had mentioned ADC12, how does 6061 compare? Well, we can see that ADC12, 380, 360, B360, and Oral 2, and we can see the copper levels increase or decrease as we go down this chart. So as we move down from ADC12 to 380, very similar copper levels. Then in A360, B360, and then Oral 2, silicon levels or copper levels continue to drop. As the copper levels drop, corrosion resistance increases. It's going to increase because we limit the amount of galvanic action that can take place with the copper in our alloys. So as we drop those copper levels, we then increase the resistance to corrosion. So the B360 and Oral 2 are going to be better at corrosion resistance than ADC 12 and 380. So just comparing the 6061 and the Oral 2, we can see similar copper levels, very low copper, 0.03 in Oral 2, 0.15 in 6061. The silicon levels are very different. So once again, the reason we don't die cast 6061 is it has very poor fluidity. Whereas if we're in that 9.5 to 11% silicon levels with Oral 2, we get good fluidity. It's a good die castable alloy. So as a quick summary, 6061 is not a die cast alloy due to its chemistry. That type of chemistry is going to lead to hot tearing during solidification and have some fluidity issues due to those low silicon levels. For corrosion resistance, 6061 is much better than ADC 12 due to the chemistry and those low copper levels. Now, as a comparison to the other alloys, Oral 2, B360, those are going to have better corrosion resistance over ADC 12 and 380. Once again, due to that low copper level. And if we wanted to get into more detail, we would have to do some more mechanical property investigation into 6061 at various temperatures as compared to ADC 12 or A380 at room temperature and then elevated properties at elevated temperatures. So that's a quick summary of a comparison of 6061 to some die cast alloys. Moving on to our next question. Question reads, we want to get your feedback on the following question. What are recommended pot temperatures for zinc, specifically Zamac 3, for die casting? We have a range of 450 degrees, 415 degrees Celsius to 430 degrees Celsius. And we're looking to confirm the set temperature and allowable range that the industry uses. So jumping right into that, the majority of die casters that I've worked with and that I've run right around that 800 to 810 degrees. That would be the pot set temperature for the Zamac 3. And as far as an acceptable range of operation, well, that really comes down to your furnace. What type of furnace you're using, what's the capability of the furnace. So with zinc, we're using steel pots, and majority of those steel pots are going to have a range of plus or minus 10 degrees Fahrenheit, or roughly 426 to 437 degrees Celsius. So if we have a larger temperature swing than that, then we're going to have some process problems maintaining consistent solidification and then controlling those defects in die casting. So whether it's zinc or aluminum or magnesium, we want consistent furnace temperatures to give us a consistent process during the injection phase of our process. So the range of operation is going to come down to what type of furnace you're using, how good are your furnace controls, what condition your pot's in. All of those conditions are going to tell us what range we're going to operate in. We want to operate in less than plus or minus 10 degrees is what we want. So as we look at the physical properties of ZA3, so this is a properties of zinc pressure die cast alloys. I have Zamac 2, 3, 5, 7, ZA8, ZA12, and ZA27. So all of these alloys are hot chamber die cast. They can be cold chamber, but are typically hot chamber. ZA27 is the only alloy on this chart that we typically would use a cold chamber process, like aluminum or mag is done in. And then when we're looking at this chart, we're singling out a Zamac 3, and then we're specifically zoning in on the solidification temperature range. So that solidification range is 728 degrees to 719 degrees Fahrenheit. That's where solidification is going to take place in zinc alloys. So even though we have this 19-degree range, when we're die casting the alloy, if we tried to cast at 719 or even 728 degrees, we're going to lose temperature. We're going to lose heat to the gooseneck. We're going to lose it to the nozzle. we're going to lose it to the sprue, we're going to lose it to the cavity. All of that heat loss is going to lead to reaching that solidification range. So we want to make sure we have a temperature, 810, 800 degrees Fahrenheit, a temperature that we can die cast, have some temperature loss, and still make a quality casting. So, depending on our cycle time, temperatures of all of those items, what's our die temperature, what's our gooseneck temperature, what's our nozzle temperature, how much heat are we going to lose to all those things, that's what's going to lead us to that final process variable, or what do we need for a furnace temperature. So for zinc, for Zamac 3, if you're running at 415 degrees Celsius, which is 780 degrees Fahrenheit, remember we start solidification around 728, by running at the lower temperature, you've got to maintain a good fill time. And if you have rapid fill and not a lot of heat loss to the process, to the tooling, then you've got a good process window and you can run at those lower temperatures. Running lower is better than running hotter. Hotter could lead to solder, it could lead to other quality defects. But if you're running at that lower temperature and you have a good process window, then by all means stay there. I was picking a temperature range, and this is in Celsius because I know you gave me the initial numbers in Celsius. I would recommend 420 to 435 degrees Celsius. That's a good operating range for the furnace. It's a good range for making sure that we have very little or low casting quality defects due to metal temperature. So I would recommend that range, and that range falls within that 800, 810 degrees Fahrenheit. Another thing I would recommend is for follow-up material, NADCA has a fairly substantial manual on die casting zinc process. So this is NADCA publication 202, and you can get this on our website, but this is going to have a lot of information on the entire die cast zinc process, hot chamber process, from the tooling to process setup to process parameters, and all those variables in between. So this would be a good reference for anybody that's doing any kind of zinc die casting. The next question is about steel. And this particular die caster sent this in and says, my customer has two specific steel types that they use to produce die cast molds, 2344 and 8407. I want to understand what these materials are and how they relate to the materials listed in the heat treat and die material specifications that NADCA has. So personally, I had never heard of 2344, 8407. So the first thing I did was I contacted them and I asked them to send me their steel specifications for those particular steels. So they contacted their customer and actually sent those steel specifications in. And then when I was discussing this with them, I also talked to them about the NADCA standards for steel in the steel types that are available in our standards. The first thing that NADCA does in our steel specification standard is we want to make sure that we get some sort of certificate of quality. So what's the certificate of conformance for all the different material types of steel? And those certificate of quality is going to talk about microcleanliness, macrocleanliness, banding, impact values, and those are all those specifications are going to be inside that NADCA publication 229, which is the 207-218 steel and heat treat acceptance standards. So this would be the list for a steel supplier. So if they were buying this steel, I would recommend that they get this kind of a list from their steel supplier, wherever they were purchasing that steel, to understand, what's the Brinell hardness, what's the chemical analysis, what's the microcleanliness level, what's the grain size, what's the banding, and then what do we need for heat treat, and then what's its impact capability. So that Sharpie V-notch testing and that impact quality is going to tell us, how resistant this material is to die steel fractures and heat check resistance. Higher impact values are going to give us more resistance to heat checking and to macro cracking or cracking of the die steel. What those CFCs look like are just going to be all of the individual specifications listed. So we have chemistry, microcleanliness, ideal microstructure, hardness, impact values, and we can see this is from a piece of OR Supreme. This is from Element Labs. Element Labs is a lab that we send die steel samples to, and they validate some of the testing provided by the steel sources. And they can do the same thing, chemical analysis, heat treatment, and so on and so forth. So for these two types of steel, once I got the specifications, I took a look at them, compared the specifications to the NADCA standards and to other known steel, found out that this 2344 has very close chemistry to a modified H11 material. So that was not an H13. And from the certificate that they sent with the from the steel supplier, it didn't tell me whether it was either going to be a superior grade or a premium grade. And once again, the difference between those is it a vacuum arc remelted or ESR electroslag remelted material? That would make it a superior grade versus just a premium grade material. So we want to understand the type of grade, not just that we have a chemistry for a modified H11. When I looked at the 8407, that had the chemistry closer to an H13 material, but once again, didn't know from the standard I received whether it's premium grade or superior grade, and I recommended to them that they make sure they get a certificate that gave us all of the listings of all of the items, so that we can then start to understand, how good of a piece of steel this is. I also asked them, if they can get all the testing done. If they got a sample of the steel, they can go to a U.S. lab and they can get that steel tested, and they can then compare that steel to the other known steel types. So we can actually take those specimens and compare those to the NADCA steel standards and get a good sense whether those types of steel will actually perform as well as the steels recommended in the heat treat specification. The other thing they need from their steel supplier is going to be the heat treat information. So not only do we want to know how it's made, but once we produce our cavity, we want to be able to heat treat this material and heat treat it correctly. So we want to know what kind of preheat it's got to go through. What's the austenitizing temperature? What's the quench and temper information that we need to make sure that we get a good quality heat treat on this material after we produce our cavity. So all of that information they would need to get from their steel supplier, the individual making the steel, so that we get good quality tool steel, so we get a good quantity of shots out of our cavities. This next question has to do with the die cast cell. So the question reads, would you be able to provide any insights on power usage for die casting equipment? They're building an R&D lab, and they're attempting to plan for future needs and/or worst case scenarios. They want to know, if we were to purchase a 30-ton or even up to 100-ton die cast machines, what are the types of electrical requirements for this type of equipment? What kind of voltage or amperage? They comment here that our lab will be running on 208 volts with 400 amps available, possibly 600 amps. Those details are not quite set in stone. So we want to once again break this question down into its individual parts. We want to understand that what kind of voltage and what kind of amperage we need, and then we want to understand the overall power requirements inside of a die cast cell. So let's talk about each one of those. So if we're dealing with equipment that's operating at 480 volts, that equipment that's operating at 480 is going to have roughly half the amperage requirements of equipment that's operating at 208 volts. Okay, so it's operating at twice the voltage, so it's going to have roughly twice the amperage required. So an example is if we have a 208 volt motor drawing 10 amps, it's going to consume roughly 2,080 kilowatts. If we have the same motor and it's now operating at 480 volts, it's going to use just over half or just under half the number of amps. So it's going to only need 4.3 amps. So if we multiply amps times volts, we can see that we're going to be consuming 2,080 kilowatts. So whether we're running at 208 or whether we're running at 480, our kilowatts are going to be the same. So our power usage, that's how a power company is going to sell you power. They're going to sell you power on kilowatts. And so the power usage is going to be pretty much identical, whether we're running at 208 and 480. So the question is, why would we prefer one over the other? So it's not because of consumption, because our consumption of power from the power company is going to be the same. So what we're really concerned about is amperage. As we decrease our voltage, as we go from 480 to 208, the amperage is going to almost double. So if we have a 240 volt motor versus a 480 volt motor, the 480 volt motor is going to draw 5 amps. The same motor at 240 volts is going to draw 10 amps. So that amperage becomes a concern because when we're dealing with power delivered, we have to, if we're having more amperage through our power lines, we have to have bigger power lines. So with a 480 volt circuit, we can have smaller, less expensive wires from our main panel to our equipment. If we're running at 208, we've got to have larger lines, so much thicker, larger transmission lines, and that's just a cost. If we're trying to understand power requirements in the die-cast cell, this is just an electrical plate on an HPM machine. This is an electrical plate off of a 250-ton die-cast machine. And we can see when we're looking at those electrical plates, it's going to tell us our voltage. So this particular machine is 480 volts, 3-phase power at 60 hertz. So that's going to be North American power. And it's telling us that the amp draw on this machine is 57 amps. So we get all of our information here, and we can see that we've got to have this hooked up to 480 volts. Now, in most cases, we have the ability to swap out the motors, and we could drop this down to 280 volts or 208 volts. So if we were dealing with this same machine, and remember we have 57 amps, 3-phase at 480 volts, if we were to run this on 208, and that's basically just the ratio of 480 divided by 208 is going to be 2.3. So we would take 2.3 times the amperage of 57 amps, and we can see that this is now going to be 131 amps for this die-cast machine. So we've just over doubled the number of amps required running this at 208. We can change out the motors, we can run this at 208, but we now have to have wiring, electrical wiring and breakers that will accommodate just running the die-cast machine at 131 amps. So when we're dealing with our die-cast cells, we're going to have a furnace, and if that furnace has any electrical requirements, then we have to understand the amperage required here. If it's a gas furnace, then it may just have a blower motor, so it have very little amp draw, but it's going to have gas that would keep the metal hot. So we need to know whether this is an electrical furnace or a gas furnace. Then we're going to have our die-cast machine and its power requirements, and then we're going to have some sort of trimming press or trim press that's going to be in the cell. Other things that can be in the cell are going to be robots. So if we have any kind of robot extraction, robot spray, we're going to have to know the power requirements of those. If we're going to have a ladle, whether we have a ladle or a Westhoven type furnace that's going to feed our metal, or if we're going to have a sprayer, and either a reciprocator sprayer or a robotic sprayer, we need to understand the amperage requirements of each one of those items. So if we're looking at the die-cast cell, we need to understand what's everything that we want in our cell, and then we basically just add all the amperage up. We take our die-cast machine, our furnace, our ladle, our sprayer, and frankly, if we were running all of these on a 208 volt cell, just these pieces could add up to over 350 amps per cell. So we would just add each one of those together. That would give our total number of amps, and we would then have to size correctly all of that electrical wiring from our main panels to our die-cast equipment. And just remember, if we were running this at 480, the amperage is going to be more than cut in half. So once again, we can have smaller lines running from our main panels to each one of our die-cast cells. So for my recommendation, I'm going to recommend that if you're setting up a die-cast cell, that you always use, a licensed master electrician to help spec out the exact wiring and the breaker box. And, what do you need to feed the entire cell? Take into account everything you want in the cell and the total amperage of each one of those items. And then always add for some expansion, because if the cell's going to be around for 5 years, 10 years, 20 years, you're going to add more things to it. You could add sensors, you could add, other pieces of equipment, degating equipment or some machining equipment. So you want to be able to just understand what you need and then size accordingly everything that's going to be operating in that cell. So for this last question, this was, once again, I mentioned this in the beginning of today, this was a little bit unusual because it's not necessarily a die-cast question. So the question reads, I'm requesting your help with a question in regards to amines in magnesium and aluminum die-cast parts. Currently, our customer requirements are asking to be amine control, which means free of any amine. And they actually sent me the drawing, and it basically just says free of any amines on the castings. And they need to understand, how is the best way to process and eliminate amines in the alloys. So first off, I'm not a biochemist. I'm a mechanical engineer, and not necessarily qualified to offer an opinion on this topic. However, I did reach out to a biochemist and a medical research professional and had a discussion on amines and how they relate to die casting and what exactly they are and how do they work. So their comments were pretty consistent between the two of them. And so when we look at casting alloys and amines, they typically do not have the ability to bond due to the lack of nitrogen compounds like ammonia in aluminum and magnesium. So their main comment was that amines can't affect you. So amines are nitrogen-based compounds, and typically like an ammonia or ammonium. And with our process, we're holding our metal, whether it's aluminum at 1250 degrees, zinc 810, aluminum will be right around 1220, magnesium 1250, zinc 810 in Fahrenheit. And typically there are not nitrogen compounds that are present. Now we do use nitrogen. We use nitrogen in our degassing process. We use nitrogen if you're using like a GISS process. And those processes actually bubble nitrogen through the molten material. But those don't necessarily form nitrogen compounds. Okay, so once again, a nitrogen compound is going to be nitrogen with some sort of hydrogen around it, and that's going to be an amine. So the castings don't necessarily have any ammonia or amines present when they're produced as a die casting. On the surface of aluminum die castings, once the casting comes out of the mold, we have the casting that's going to form an aluminum oxide layer, and it forms almost immediately after the casting is removed from the die casting machine. So once again, we now have this aluminum oxide that these amines can't necessarily bond with. So the biochemist did comment that amines can bond ionically with inorganic materials. So they can form an ionic bond, not a covalent bond with inorganic materials. So his comment was that if we had the correct ionic bond charge on our casting, there potentially could be a bond if amines were present. His further comment is that this is highly unlikely, as because most amines bond chemically, like amino acids and ammonia, and they don't necessarily bond in an ionic fashion. So in summary, I'm going to say, don't use ammonia, don't use ammonium on any post-treatment of the die castings. Have the die castings made, you trimmed it, you're prepping that casting, make sure that any cleaning solutions don't have ammonia or don't have any type of ammonia compounds in them, and then that's going to eliminate any amines from actually just laying on the surface, being present on the surface, or any potential ionic bonds that could form if we had the correct charges, positive and negative charges between those different items. So that's all the questions I had for today. If you have additional questions, you can send them in to me personally. You have questions, you can put them on our website. My email is listed below, and you can email those questions to me. I will get you those answers, and we can have those on our next edition of Just Ask Paul. Hope everybody enjoyed today, and I thank you for attending.
Thank you, Paul. So as Paul said, we're going to open up for questions. There are a few ways that you can ask questions. Within your control panel, there's a text box. If you click within the text box, type your question and hit send, we will get that in on our end. The next thing that you can do is if you're calling in on the phone or if you have a mic set up, just click that little hand icon. We'll go ahead and unmute you and you can ask your questions out loud. Last but not least, please feel free to email us. You can either email just your confirmation email to Nanka directly, or you can contact Paul. Again, there is a dedicated website for you to be able to submit any additional questions that you might have that you'd like to see featured on this webinar series. And we urge you to send those in anytime you're thinking of them. It doesn't have to be a specific date where you submit that, just any question that might pop up that you think would be of interest to get an answer to. So with that, we're going to hang on the line for a few minutes here. As always, after this recording will be converted. It will be set up online for you to be able to download and share with others as well. So with that, we're going to hang on the line and see if any questions come through. All right, I don't currently see any questions coming in. If you're in the process of typing in a question, if you could click that little hand icon, that'll just let us know that you're in the process of typing something in, and that we should hang out on the line until that comes through. All right, I don't see any hands raised and I don't see any questions coming through. So with respect to time, I am going to say thank you all for attending. And Paul, thank you for presenting today. And we look forward to seeing you on the next episode of Just Ask Paul. Thanks, guys. Have a great rest of your day. Bye.